Have you ever picked up a stone on a beach or a mountain trail and wondered about its journey? It sits silently in your palm, cool and still. Yet, what if it was not so silent? What if this very rock held within its structure a memory of everything it has ever witnessed? Imagine a world where every stone is a library, a chronicle of deep time. This is not mere fantasy. In a very real sense, rocks do remember. They carry the imprints of colossal forces and of ancient environments. They are the Earth's oldest storytellers, waiting patiently for us to learn their language. The story of our world is written not in ink, but in stone. It is a tale of continents, drifting mountains, rising oceans, forming and vanishing. These grand narratives are captured in the layers of sediment, the twist of a mineral vein, the very fabric of the crystals that make up the rock. Every grain of sand on a dune has a history. Every pebble smoothed by a river has been shaped by the ceaseless flow of water. These are archives of time itself, holding the key to understanding the world we inhabit. Consider the sheer scale of this geological library. The ground beneath our feet is a tapestry woven from countless such stories. They are the Earth's oldest storytellers, waiting patiently for us to learn their language. Let us begin with a truly remarkable phenomenon, a secret spark hidden within many common crystals. It is called the piezoelectric effect. Imagine holding a crystal such as quartz in your hand. If you squeeze it, even with immense pressure, it generates a tiny measurable electrical charge. This is nature's own little generator. The pressure realigns the atoms within the crystal's structure, creating a positive charge on one side and a negative charge on the other. It is a direct conversion of mechanical energy into electrical energy. This effect is not just a one-way street, it works in reverse as well. If you apply an electrical voltage to that same quartz crystal, it will physically change its shape. It will bend or vibrate with incredible precision. This is the principle that powers the quartz watches on our wrists. A tiny battery sends an electrical pulse to a quartz crystal, causing it to oscillate at an exact frequency, which is then used to keep perfect time. So, this hidden property of rocks is not just an ancient secret, it is a part of our modern daily lives, a quiet partnership between human ingenuity and the fundamental laws of nature. Now let us imagine this process on a planetary scale. The Earth's crust is full of quartz and other piezoelectric minerals. When tectonic plates grind against each other, they are squeezing these rocks on a colossal scale. Could this generate vast electrical fields deep within the Earth? Beyond the spark of electricity, rocks hold another equally profound memory, a magnetic one. Think of it as an ancient compass, frozen in time. Many rocks, particularly those born from cooling lava, contain tiny particles of iron-rich minerals like magnetite. When lava is molten and hot, these microscopic iron particles are free to move. Like tiny compass needles, they align with the Earth's magnetic field at that specific moment. They all point the same way, toward magnetic north. As the lava cools and solidifies, this alignment locks in place. The magnetic particles are frozen, unable to move again. The rock now carries a permanent record of the direction and strength of Earth's magnetic field at formation. This is called paleomagnetism. By studying these rocks, scientists read that frozen compass and determine where the Earth's magnetic poles were located millions of years ago. It's an extraordinary glimpse into Earth's deep past. This magnetic memory helped prove plate tectonics. Rocks of the same age on different continents pointed to different magnetic norths. It was a puzzle. The only explanation, the continents moved. Rocks formed in one place then drifted across the globe. Those reversals are recorded on the ocean floor as striped magnetic layers. That seabed barcode lets us measure seafloor spreading from mid-ocean ridges. The rock's frozen compasses aren't just remembering, they provide a detailed, dated account of how the planet's surface was created. The Earth is a restless planet. Its crust is a mosaic of massive plates constantly pushing, pulling, and grinding against one another. The immense forces involved in these movements leave their scars directly on the rocks. When an earthquake strikes, it is not just the ground that shakes, the very structure of the rock is altered. Rocks along a fault line can be shattered, pulverized into a fine powder known as fault gouge. Or they can be polished smooth by the friction of the two sides sliding past each other, creating a surface called a slicken line, which is often grooved, showing the exact direction of the slip. These features are the direct physical evidence of past seismic events. A geologist can walk along an ancient, inactive fault and see these signs clearly. By studying the slicken lines, they can reconstruct the movement of a quake that happened millions of years ago. They can see the layers of fault gouge that indicate repeated ruptures over time. These rocks become a ledger of tectonic violence. a minute-by-minute account of the planet's cataclysmic adjustments. They tell a story of immense stress building up over centuries, released in a few terrifying moments of motion. One of the most fascinating ways rocks record earthquakes is through the formation of pseudotacholites. The name sounds complex, but it describes something dramatic: fossilized earthquakes. During a particularly violent and rapid slip along a fault, the friction can generate so much heat that it melts the rock itself. This molten rock is injected into surrounding fractures, where it cools quickly to form a dark, glassy vein, a snapshot of the earthquake's peak intensity. Volcanoes are, one of nature's most spectacular and creative forces. They are the gateways to the Earth's molten heart, bringing new rock to the surface, and as this molten rock, or magma, cools, it becomes a detailed diary of the eruption itself. The minerals that form within the cooling magma are the words in this diary: the size, the shape, the composition. They reveal how quickly the magma cooled the pressures it was under and the chemical ingredients it contained. It's kind of like a recipe from the Earth's kitchen, preserved for us to read. For instance, if magma cools very slowly deep underground, it allows large, beautiful crystals to grow. However, if magma erupts explosively and cools rapidly in the air or water, there is no time for large crystals to form. This creates volcanic glass like obsidian or rocks with microscopic crystals like basalt. A single volcanic rock can even tell a story of two-stage cooling, with large crystals that grew slowly deep down, suspended within a fine-grained matrix that cooled quickly upon eruption. As crystals grow within the magma, they can trap tiny bubbles of the original molten rock or the volcanic gases that were dissolved within it. These are called melt inclusions and fluid inclusions, tiny time capsules. By analyzing these inclusions in a laboratory, scientists can determine the temperature, pressure, and gas content of the magma chamber miles beneath the surface. For billions of years, the stories written in stone were tales of natural forces of drifting continents erupting volcanoes. But now, a new author has begun to write its chapter. And it's doing so at unprecedented speed. That author is humanity. Our activities are leaving a distinct and permanent mark on the geological record. We're creating new types of rock and materials that will be preserved for millions of years. Future geologists will read our strata and see a clear, unmistakable signal. Consider our cities. We produce vast quantities of concrete, an artificial sedimentary rock. It is made of cement, sand, gravel, bound together to last millennia. Far future geologists might find layers with fragments of brick asphalt, glass, plastic, fused together. They've named one of these mixtures plastiglomerate. It's a fusion of natural debris like sand and shells with molten plastic, now found on coastlines worldwide. The chemical signature of our age is unmistakable. Fossil fuel use and industry have released unique elements and isotopes that settle into lake and ocean sediments. Spikes in nitrogen from fertilizers, carbon from burning coal and oil, and rare radioactive elements from mid-20th century nuclear testing will be datable markers. These layers tell of a species that harnessed immense energy and altered the planet's chemistry. This new layer is called the Anthropocene, the age of humans. It's sobering. Rocks have always recorded history, but ours is a story of rapid global change. The ground beneath our feet is no longer only nature's record. It has become a mirror of our lasting footprint. The stories held within rocks are written in a language of minerals, chemicals, structures. The process often begins in the field, with a geologist's hammer and a keen eye. A skilled observer can look at the layers in a road cutting or a cliff face and read the basic sequence of events. Ancient riverbeds, volcanic ash layers, tilt and fold of rocks. This initial observation is the first step in deciphering the narrative. Back in the laboratory, the real deep reading begins. To see the microscopic details, geologists cut rocks into slices so thin that light can pass through them. These are called thin sections. When viewed under a petrographic microscope, which uses polarized light, the different minerals within the rock light up in a dazzling array of colors. This allows scientists to identify each mineral and observe its relationship to its neighbors. They can see the fine textures that reveal how the rock formed, whether it cooled slowly or cooled quickly, or if it was squeezed and deformed long after its creation. To uncover the chemical secrets, even more advanced tools are used. A device called a mass spectrometer can measure the precise amounts of different elements and their isotopes within a rock sample. This is the key to radiometric dating, the technique that allows us to assign an absolute age to a rock. By measuring the ratio of a radioactive parent isotope to its stable daughter isotope, like uranium to lead, scientists can calculate how much time has passed since the rock solidified. This gives us the dates for our geological calendar, allowing us to pinpoint the age of fossils, volcanic eruptions, and other ancient events. These methods, and many others like them, allow us to listen to the stone with ever-increasing clarity. We can analyze the magnetic memory with magnetometers, probe the atomic structure with X-ray diffraction, and read the story of past climates from the chemical composition of fossil shells. By listening to the rocks, we have been able to reconstruct worlds that are almost beyond our imagination. The stones tell us of times when the Earth was a fiery, molten ball, and of an era when it was covered almost entirely in ice, a snowball Earth. They hold the fossilized remains of the very first single-celled life, tiny organisms that began the monumental task of filling the atmosphere with oxygen. Every fossil is a story captured in stone, a snapshot of a life form that existed for a time and then vanished. The rocks of the Carboniferous period, for example, tell the story of a world covered in vast, swampy forests. The plants of this era were giant ferns and club mosses, and the air was rich with oxygen. When these plants died, they fell into the swampy water and did not fully decay, eventually becoming compressed into the vast coal seams that would one day power our own industrial revolution. The very rocks we burn for fuel are the preserved remains of an ancient alien forest. Every fossil is a mineralized echo for us to find. In another chapter, the chalk and limestone deposits around the world tell a story of warm, shallow seas. These rocks are made almost entirely from the microscopic skeletons of countless trillions of marine organisms. Their tiny calcium carbonate shells rain down on the ocean floor, accumulating in thick layers that would eventually become rock. When we see the white cliffs of Dover, we are looking at a cemetery of unimaginable scale, a testament to the power of tiny life forms to build geological features that are visible from space. These are just a few of the countless tales that have been unearthed. Rocks have shown us evidence of colossal asteroid impacts that changed the course of evolution, like the one that led to the demise of the dinosaurs. They have revealed the cycles of ice ages and the scratches left by glaciers on bedrock. So, the next time you walk outside, take a moment to consider the ground beneath your feet. It is not just dirt and stone, it is a library, an archive of unimaginable antiquity, holding the memory of everything that has come before. Every mountain range is a story of collision and uplift. Every canyon is a story of water and time. Every grain of sand on every beach is a tiny, polished word from a story that began hundreds of millions of years ago. The history of our world is not confined to museums, it is all around us. This understanding transforms our perception of the world. A simple stone is no longer just a stone, it is a time capsule, a witness to deep history. It may have been born in the heart of a volcano, traveled with a continent, been buried miles beneath the surface, then uplifted and eroded to finally rest at your feet. It connects us directly to the immense powerful forces that have shaped our planet. The silent stories told by these broken and melted rocks provide the crucial knowledge we need to coexist with our planet. It reminds us that our time on Earth is a fleeting moment in a story billions of years old. This great stone library is still being written. The Earth continues to shift, volcanoes continue to erupt, and sediments continue to be laid down in the oceans. And we too are now writing our own chapter in the Anthropocene, leaving a message for the far future. The rocks will remember us, just as they remember the dinosaurs and the ice ages. What will the geologists of a distant time make of the layers we are creating? All it asks of us is that we learn to listen, to look with curiosity, to ask questions, and to marvel at the epic story written in stone.